welcome to Coding with A. And in today's episode, we are going to talk about low level design. And from this video on, I'm going to start a series on low level design where we'll be covering concepts on low level design and we'll understand more about low level design and how it's done. This subject is very important because most of the time this is asked in interviews, and a lot of us are usually not prepared because we only revolve around DSAs and core subjects that we forget to learn about low level design. Before understanding about low level design, we obviously know what an SDLC is: software development life cycle, where the overall architecture and structure of a software system or an application are planned and documented. Now, this is very important. Like, the software development life cycle is very important because it bridges the gap between the requirement specification and the actual implementation of the system. Now, the primary goal of this high level design is to create a blueprint or a roadmap for the software that guides the development team in building a system that meets the desired functionality, performance, and quality as per the requirements of the stakeholders. Now, so as we all know, we'll have a few steps in software development life cycle, like the requirement gathering, then the analysis, then designing stage, and then we construction of the software system, and then testing, and then maintenance of the overall system. Where does low level design come into the picture? Now, this high level design refers to the conceptual and architectural phase. Okay, it's all about architecture and components and the overall functionality and the user experience. This doesn't really give us any implementation details of the software. But low level design, on the other hand, involves detailed planning of each component or module that is outlined in a high level design. Okay, so we'll have several components and structures that are highlighted in the high level design. But we are not told the implementation details. So, because everything has its own job to do. So, the job of the high level design, or its role, is to give a roadmap that doesn't delve into the specifics. But the low level design, on the other hand, takes the roadmap and then gives implementation details for each component or module that is mentioned in a high level design. As you can see here, now this is like a structure of a software system with some components in it where the architecture and everything else is defined. And if you look at the low level design here, two components are taken, A and B, and the implementation here is shown. Now, this high level design, like all of this, is usually planned by the architects. Okay, the design, the requirement analysis, and giving an outline of the whole software system is developed by the architects. But the actual implementation of the software as per the high level design is done by the engineers. Now, how does this low level design help us? This low level design helps us in requirement gathering, readable and understandable code. It is extendable. It makes the software system extendable, and it also makes the software system maintainable. Now, what exactly is the requirement gathering here? In requirement gathering, all the requirements that are needed for a software system to be built are discussed with the stakeholder or the client. Now, after this low level design helps us make a readable or understandable code. Now, code can be written by everybody, but what makes it stand apart is its quality of being readable and understandable. That is very important when writing a code. Now, another important thing is this low level design helps us achieve extendability, which is nothing but able to add new features to an existing code base without having to modify other stuff in the database. So you can still add something to a database or the code base without having to modify other components. That is how low level design helps us. And the last thing is to keep it maintainable, which is by easy to keep the current system working, which is like including fixing bugs and making updates to the code base and etc. Now, this low level design here ensures modularity, single responsibility, dependency injection, abstraction, and interface design. Modularity is nothing but module. What is module? It's a small unit in a code component. Now, how this low level design helps us is that it ensures testability. Okay, this enables unit testing and isolated code components. Now, instead of having to test on a whole thing, since we'll have small modules in a given component, it makes us easy to focus on unit testing rather than a whole integration testing. Though we have unit testing and integration testing both in low level design, but given that we get to make this into smaller components or smaller modules and then test on each on one of those, if there are any faults or if any requirements don't match, it is easier for an engineer to rectify. Now, second thing is the single responsibility. Now, what it does is that it simplifies testing by assigning clear responsibilities to modules or classes. Like, I'll give you an example. So, if there's a module A and if there's a module B. Now, A has to do its own job. There could be a bigger component C where it can perform the jobs of both A and B. But when a problem comes, it will be hard to identify which part of it is causing problem in C. So rather what we do is that we take single modules for each of those, assigning single responsibilities such that the responsibilities for A would be clear with respect to A and for B would be clear with respect to B, such that the testing becomes easier. So in case A fails, we'll know that the problem is within A. But if C fails, it will be hard to identify whether the problem is within A or B. Next is the dependency injection. Now, this dependency injection helps us facilitate the mocking or stubbing for the unit tests. Okay, it helps us facilitate the mocking or stubbing for unit tests. Next is the abstraction. Abstraction is nothing but it abstracts the actual logic from the end user. It hides the implementation details. Though we focus on the implementation details, it is not necessary that the end user has to know what the implementation logic is. Now, the last one is the interface design. Now, this ensures that integration testing through well-defined interfaces and contracts is done. So, we know that we perform unit testing because it makes the single responsibility easier. But after combining all the modules back into one single entity, so the integration testing will obviously be done on it. And this interface design, it will ensure that testing through well-defined interfaces and contracts. Now, since this low-level design is handled by engineers, let's see what actually an engineer does during the low-level designing. Now, this low-level designing, like the engineers, they translate the high-level architectural design into detailed implementable specification for each module. So, as discussed above, you will be given that, okay, so for example, if I take an example of booking a ticket for a cinema or a movie. So for a movie, a detailed outline will be given that, okay, there will be 5 floors, there'll be a booking counter, people will come, there's a door, people will leave, there's a screen, people will watch, there's a projector. But how do they book the tickets? How can people be allotted screens? The architecture is all about, oh fine, so how much space do we need for the cinema to be there, and how do we issue the tickets? What algorithm do we use to issue the tickets? So is it like first come first serve basis, or do we like make it in terms of cost? So all of this is all about high level design. But in low level design, you show the implementation, like that algorithm that is being implemented while giving tickets or while giving the seats or while assigning the screens for a particular movie. Now, next is they take the architectural blueprints provided by the architects and design the internal structure, data flow, algorithms, data structures and interfaces of the software components. Now, we know that they take the blueprint and they convert that into an implementation. Now, how do they make it into an implementation? How do they design it? By using data structures, algorithms, interfaces and data flows. For example, you are standing at a ticket counter. You are buying a ticket. Now, there are 6 people standing. Now, you use a queue to give tickets to the member, correct? For the customer who has come to collect a ticket, you give, people are standing in a queue manner. Now there you use a queue for the order of people to assign a ticket. So queue is a data structure here. Now instead of queue, if you use a stack, what happens? What does stack follow? It follows first in last out or last in first out. But does it work that way? Now if I go to the theater first, I'm supposed to get the ticket first. Now, which data structure follows this thing? It follows queue. So it is very important that the appropriate data structure is to be used, which is our third point. Now choose appropriate data structures such as arrays, linked lists, hash maps or stacks and queues, and algorithms, example sorting, searching algorithms based on the performance requirement and data manipulation needs. Like I was giving you an example earlier, where if I go to a movie theater and I'm standing in a queue, I would definitely want to collect a ticket for myself first than the person who has come later. So in this case, we use a queue to keep people in that queue. Okay, I know that now this person A is first in the queue, then comes B, then comes C. Now I can't randomly give a ticket to person C. Okay, that's where all this implementation part comes in. Now the last thing is implement design patterns like singleton, factory, observer, decorator to address specific design challenges and promote code reusability. Now we'll talk about these design patterns later in the videos, like upcoming videos, but to give you a small overall understanding of what a design pattern is. So these design patterns are nothing but the patterns like the solutions to a common problem that help us in designing efficient and reusable code, which is something that all the developers strive for. Now, when usually working on large applications, code structure becomes an integral element where we need to prevent the repetition of the code for similar tasks. Correct? Like you can't use the same code, you can't write the code 100 times where there's a similar situation. So in that case, what you do, you write a piece of code and make sure that can be reused and in other parts of the code, and you also write it in such a way that it's easily adaptable in the future. In such scenarios, having a structure that could be used to solve various common issues, that is where the design patterns come into the play. Now, this is about today's video, and for us to learn more about low-level designing, the next part is to learn about the pillars of OOPS. The pillars of OOPS. We all know what the 4 pillars of OOPS are, and we'll learn more about those in our next videos.